Alright, welcome back. Last time we talked about why operating systems exist and went over some history. I did want to touch upon the fetch, decode, execute cycle and process virtualization in this video, which are important concepts, but I figured they're pretty straightforward and you can get the gist of it after reading the material just once. So in this video, I'll be focusing on topics from chapter 4 and 5 from the OSTEP textbook and help you understand what a process actually is under the hood, how the OS creates one from scratch, and also I'll get into the system calls or Syscalls as they're called, which make Unix what it is. Let's go. So last episode I said a process is a running program. And that's true, but it's worth being more precise. Because a program and a process are not the same thing. A program is dead. It's like a file that's sitting on your desk with a bunch of instructions and maybe some static data. It does nothing by itself, so it's kind of like a recipe book that's collecting dust on a kitchen shelf. A process is what happens when someone actually picks up that book and starts cooking. It's the live running instance of that program. And just like you can have two people cooking the same recipe simultaneously in different kitchens, you can have multiple processes running the same program. So when people say Chrome is a process, well, technically Chrome might be like 50 processes. Each tab could be its own process running the same browser code but in different states. The program is one, but the processes are many. Okay, so if a process is a running program, what does the OS actually need to track about it? What information defines a process at any given moment? This is called the machine state, and it's basically a snapshot of everything that the process touches. There are three big pieces that you'll have to remember. First, memory. Specifically, the process's address space, or the chunk of memory that it's allowed to access. This contains the code, which is the actual instructions, the static data, which is the global variables and constants, the heap, which is dynamically allocated memory, think about malloc in C language, and the stack, which contains your local variables, function parameters, and return addresses. The heap grows downward and the stack grows upward, or vice versa depending on the architecture. So they grow towards each other, and if you find that they ever meet, congratulations, you've seg-faulted. So when you run a bunch of code and VS Code throws you a segmentation fault, it's basically just this. Second, registers. The CPU's registers are part of the process state. Most importantly, the program counter determines which instruction we are currently on. The stack pointer determines where the top of the stack is, and all the general purpose registers hold intermediate computational values. The OS needs to store every bit of information about a process which it needs for reconstructing it again after a context switch. The process never even knows it was paused. Third, we have the I/O state. This is basically what files the process has open. In Unix, every process starts with 3 open file descriptors by default. First is the standard input, then we have the standard output, and finally the standard error. The descriptors for these are 0, 1, and 2. These are how your program reads from the keyboard and writes to the terminal. We'll come back to why this matters when we talk about I/O redirection later. So how does the OS actually create a process? What happens between you double-clicking an app and it showing up on the screen? This can be broken down into 4 steps. In step 1, the OS loads the program's code and static data from the disk into memory. In ancient operating systems, this was done eagerly. The entire program loaded all at once before anything ran. Modern OSs are lazier. They use techniques like paging and demand loading to only pull in the bits that they actually need and when they actually need them. This is actually way smarter, and we'll cover that when we hit memory virtualization. But for now, just know that code goes from disk to RAM. Step 2. The OS allocates a stack and initializes it. It sets up argc and argv, the arguments to the main function. This is literally why your C programs have int main and those things inside the brackets. The OS put those there for you. Step 3. The OS allocates some initial heap space which is small at first, but when your program calls malloc, the OS may get involved to give it more memory. When you call free, you're returning that memory. So if you forget to free the memory, that's called a memory leak. Your program is basically hoarding memory like a digital dragon that's sitting on a pile of unused RAM. Step 4. The OS sets up I/O, which is, it opens up those 3 default file descriptors that we talked about, and in step 5, the OS jumps to the main function. It sets the program counter to the entry point of the program and hands over control of the CPU. Great, now the process is alive and running. Now the OS needs to give us, that is the users and programmers, a way to actually interact with these processes. The textbook calls this the process API, and it boils down to 5 basic operations that any OS needs to support. Create. Make a new process. You could double click an app, type a command in the shell, whatever. Next we have destroy. That is, we need to kill a process that's misbehaving or that you just don't want anymore. That could be you doing a Control-C on the terminal, typing in a kill command, or just opening up the task manager. Then we have wait. Sometimes a process wants to pause and wait for another process to finish before continuing, like a parent waiting for a child to come home. And that analogy is literal here, by the way. Then we have miscellaneous control, which is suspend, resume, stuff like that, and status. How long has this been running? What state is it in? Or is it even still alive? These 5 things are the interface. Now let's see how Unix implements them. Before we jump to the syscalls, just one more thing from chapter 4. The OS is just another program, and so like any other program, it has its own data structures. The main one for process management is called the process list, or sometimes the process table. Each entry in this table is called a process control block, or a PCB. This is basically a struct that holds everything that the OS knows about one process. In xv6, this struct is called proc. It contains the process's memory pointer, its size, its kernel stack, its state, its PID, a pointer to its parent process, the open files that it has, its current directory, and critically, its register context. The register context is important because that context struct holds saved register values, EIP, ESP, EBX, and so on. When the OS context switches away from a process, it dumps the registers into this struct. And when it switches back, it reloads them from here. That is the mechanism behind this illusion. Notice those extra states beyond running, ready, and blocked? Embryo is a process that is being born. It's in the middle of being set up by the OS. Here you can recall all those steps that we just went through earlier. Zombie is a process that's dead but hasn't been cleaned up yet. Nobody has marked it as done. It has finished executing, but its parent hasn't yet called the wait function to collect its exit status. It's just kind of hanging around undead, clogging up the process table. It's a very fitting name. Okay, on to chapter 5, the process API in Unix. But first, what is a system call? A syscall is how a user program asks the OS to do something that it can't do on its own. Your program runs in the user mode. It's sandboxed, limited, and can't directly touch hardware or other processes' memory. But sometimes it needs the privileged operations to create a process, to read a file, to send network data. So it makes a system call, which is essentially knocking on the OS's door and saying, hey, I need you to do this thing, but you haven't really given me the privilege for it, so I'm asking you to do it. The OS switches to kernel mode and does the thing and returns the result. We'll go deep on this mechanism, which is limited direct execution, dual modes, traps, and all of that in the next episode. For now, just know that syscalls are the bridge between your code and the operating system. Alright, the big 4. Firstly, we have fork. Fork function is the strangest function you will ever call. Here's what it does. It creates an almost exact copy of the current process. The same code, the same data, same stack, same program counter, same everything, except now there are two processes. The original process from which you forked is the parent. The copy is called the child. And here's the weird part. Fork returns twice. Once in the parent, where it returns the child's PID, and once in the child, where it returns 0. Those values are important. That's how you tell which one you are. And here's the kicker. After fork, you don't know who runs first. The parent might run first or the child might run first. It's non-deterministic. The scheduler decides and the scheduler does not care about your feelings. I'll make a separate video going over some fun trick questions with the fork function. Like what happens when you fork inside a loop and how many processes get created when you do that. All that stuff. It's basically a puzzle game at that point, which makes it really fun. Next, we have the wait function. So if the parent wants to guarantee that it runs after the child finishes, it calls wait. Wait blocks the parent until one of its children terminates. It returns the PID of the child that finished. This makes the output deterministic. The child always finishes first and then the parent function continues. Determinism has been restored. There is also wait PID for when you want to wait on a specific child function and not just any child function. This is useful when you have forked multiple times throughout your process. The next thing that we have is exec. So fork gives you a copy of the same program, but what if you want to run a different program? That's exec. Exec replaces the current process's code, data, stack with a brand new program. It loads the new program from disk, reinitializes the stack and heap, and starts executing from the new program's main function. The PID stays the same. That is an important point to note. The process identity is the same, but the content that is being played is completely different. It's like a body swap in a movie. Same person on the outside, but entirely different on the inside. And here's the critical thing. Exec never returns. If it succeeds, the old code is gone. There's nothing to return to. That printf after exec in your code, that is dead code. It only runs if exec failed. So if you see a question in the exam where there's a print function after an exec call, just trust that that print function will never print anything. Now, here's the genius of the Unix design. Fork and exec are separate calls. Why? Because the gap between fork and exec is incredibly powerful. In that gap, you can set up the child's environment before the new program starts. Redirect file descriptors, set up pipes, change permissions. The new program doesn't even know that happened. And this is exactly how the shell works. Next, we have the kill function. Kill sends a signal to a process. Despite the name, it doesn't always kill things. It sends a signal and the process decides how to handle that signal. Now, if you used kill with sig term, it's a polite way of saying please terminate, and using sig kill means that you're telling the process that you're done and there's no negotiation there. There's also sig stop to pause and sig cont to resume. Processes can catch and handle most signals with signal handlers, except sig kill. That one is the OS playing judge, jury, and executioner. No appeals. With fork, exec, and wait, you now understand how a shell works. When you type ls with the flags of L and A and hit enter, here is what happens. The shell calls fork to create a child. The child then calls exec to replace itself with the ls program. The parent calls wait to sit there until ls finishes. And when ls exits, wait returns and the shell prints a new prompt and waits for your next command. That's literally it. That is the shell that you run on your computer. It's just a while loop of fork, exec, and wait. One last concept before we wrap. The textbook makes a distinction between mechanisms and policies, and it's actually a really elegant design principle. A mechanism answers how. How does the OS perform a context switch? How does it create a process? These are low-level nuts and bolts. A policy answers which process should run next, which page should be evicted from memory. These are high-level decisions, and the beauty is that they're separate. You can change the scheduling policy to round-robin, priority-based, or whatever, and you wouldn't have to change the context switch mechanism. Alright, that's chapter 4 and 5 of the textbook in one shot. You now know what a process really is, what the OS tracks about it, how it's created, the process API, and the 4 big syscalls. In the next video, I'll go over the shell, redirection, pipes, and chaining. But the huge question we've been dodging is this. If the OS gives the CPU to a user process, how do we get it back? How do you prevent a rogue process from just hogging the CPU forever? The answer involves limited direct execution, dual modes, and the hardware mechanisms that let the OS regain control. It's where the OS stops being a polite manager and becomes a bouncer. See you there.